There we go. Now I can get it back. Okay, showtime. Welcome back to class. Welcome back to the basement. I am very optimistic that Tuesday we will be back in person for one brief shining moment until we get kicked out of our classroom on Thursday for comprehensive exams. So there are 2 dates this semester that I had noted on the syllabus as Zoom only question mark, and I confirmed with the scheduling that we do in fact lose our classroom on Thursday, September 7th, and at sometime in late October. So those dates are on the syllabus. I updated the printable version of the syllabus and the online syllabus accordingly. So in person on Tuesday next week, hopefully, and not on Thursday. Speaking of online activity, so I looked at my YouTube videos this morning, as I tend to do, just to make sure that people can find them. If I don't have any views, I figure I've done something wrong. And the one from Tuesday had over 400 views. Normally they have like 20 to 30 each week. And I know there are not 400 of you. And I highly doubt you would have watched Tuesday's video, 20 times a piece. So I'm kind of confused on this score, but if anyone out there on the internet can shed some light as to why my channel has suddenly gone like nerd viral, I would be interested to know. I don't know, like 400 is viral for me. So Garbage Day worldwide. Indeed, happy Garbage Day to those of you from, Solon, Oxford, and surrounding communities. Anyone else having Garbage Day today? No? Okay, fair enough. I remember when I lived in an apartment, I didn't have to pay attention to such things. I just took my garbage out and then it just magically disappeared. So those of you who are in that situation, good. All right, so last time we were talking about empty models, interclass correlations, other fun things that you can compute out of an empty model. We started talking about how to evaluate whether or not you actually need 2 different piles of variance, whether you need a level 2 random intercept variance for cluster differences as a likelihood ratio test. Do you remember the gist of that? Maybe? The idea is that every model... Oh, go ahead. I heard a voice.
So, I'm sorry.
No, please.
I had a question back on slide 17. I made a note, and I just wanted to double check that it was right. In those single case designs, or those N of 1 designs, I believe you had noted participants are level 2 and the repeated observations are level 1. I just wanted to make sure I had that right and not flipped.
Yes. So in that type of single case design, I'm finally going to learn that word. This is directly analogous because the observations that you have are sort of clustered within a person. There are maybe more observations that happen within like a baseline period, so to speak, where you wouldn't expect any systematic change. And those observations would be thought of as exchangeable in the same way that kids from the same class might be thought of as exchangeable. So if you want to know, how many observations do I need in order to get a good estimate of someone's baseline value, where good is operationalized as a reliability coefficient, this ICC2 can help you to try to anticipate that. So yes, directly analogous.
Awesome. Thank you.
It is awesome. It's some cool stuff, huh? Yeah. So the interclass correlation 1 tells us what proportion of variability is at level 2 between cluster mean differences. Interclass correlation 2 describes the reliability of any cluster's mean across the people in that cluster. And in order to detect whether or not we need this random intercept variance in terms of a significance test, we do that as to what extent does it improve the model. The way that's operationalized is our friend the likelihood ratio test, which was on slide 21 here. So every model that you estimate will come up with a value that's known as a log likelihood. What that is the sum across observations in your data set of how tall the model parameters make that unit's data, where tall is defined by some kind of probability distribution. In these models, it's going to be multivariate normal for most of the class until we get to the generalized unit. So each cluster has a set of observations, and using the multivariate normal distribution, we compute a height for how likely those observations are given the best estimates of our model parameters. Each cluster gets a likelihood as a height. in order to avoid having to multiply them, because those are tiny numbers that get even tinier when multiplied, we take the natural log of that. Then that allows us to add all those values across clusters, and that summary is called log likelihood. So that's your index of model goodness, so to speak. Because we are going to eventually take the difference in log likelihood and multiply it by -2, some software programs start with that as the base that it uses to report. So -2 times the log likelihood of the model is output in some programs such as SAS and SPSS. Regular log likelihood is output by Stata and M+, and depends on which package you're in R. And so the difference between -2 log likelihoods is distributed as a chi-square, where the degrees of freedom for that is the number of parameters that you've added. In this context, if you're only talking about whether you need a random intercept variance, then that's one parameter, because it's one variance. So it doesn't matter how many clusters you have or how many people you have, it's one new parameter because it's the variance across clusters is what the model parameter becomes. And this type of idea of comparing log likelihood is ubiquitous across many different types of models and areas of statistics. So this is something that you'll see again and again if you haven't already. And I have a side note on here. In the situation in which you are using this test to ask whether a variance is necessary, because the variance can't go lower than 0, a mixture distribution is more appropriate, so that lowers the critical value for what enough of an improvement is to be declared significant. So I will show you all of that in the example that we have forthcoming today. So we looked at that in the example in here. So the difference, for instance, in -2 log likelihood for my token example here, before versus after adding a random intercept variance at level 2 was a test statistic of 400 and some odd. Yes, highly significant. Definitely we need the random intercept variance, which is not unexpected since it was 22% of the total variability. All right, I think that's where we left off, starting to talk about flavors of maximum likelihood, if my memory serves. Any other questions or things you want to review or ask about before we head into new territory? Can you still hear me? I'll ask that question. Excellent. Please let me know if the microphone craps out. I hope to fix it as efficiently as I was able to last time. My mouse is spinning. That's never a good sign, but we'll see what happens. All right. So picking up then on slide 24 of lecture 2, one other thing that you'll need to keep in mind in making sure that you are doing likelihood ratio tests correctly is the distinction between maximum likelihood, as it is typically known, and an alternative version that we are going to use in this class most of the time, which is called restricted or residual maximum likelihood. These are both what are known as full information techniques, by the way. So sometimes you will see maximum likelihood abbreviated rather than ML as FIML or FIML as it is pronounced. For whatever reason, REML, as it is abbreviated for this one, doesn't have the FI in front of it when people say it, but it should because it's full information. So you could say FOREML if you wanted to. What the term full information means is that it uses all of the original data in building the likelihood function. So that allows you to include cases that have missing data to some extent because you're building a likelihood for each cluster. So if you think about different numbers of people per cluster, that's kind of like missing data in that some clusters might have 30 spots and other clusters might have 10. So not every case has to have the same number of observations. Residual maximum likelihood is directly analogous to ordinary least squares in terms of how model variances are computed. So in regular old linear model regression land, we would have variability left over. So for instance, this little formula here, what y for each case got minus what it was supposed to be according to the model fixed effects, square that, sum it over, and then divide by n minus k, where k is the number of fixed effects. So this is directly analogous to what you'd get in the sum of the squares table, where you're taking into account the fact that you had to know what the fixed effects were before you could figure out how much variability was left over. So this is the same thing. If you were to use residual maximum likelihood to estimate a general linear model, you would get the exact same output out as if you just used regular regress or linear models or what have you. This is only available, though, for models in which all of the residuals are supposed to be conditionally normal. So in multi-level models, that means the level 1 E's are normal and the level 2 U's, the random effects, are also normal. If you are in any other kind of situation, you are stuck with regular flavor maximum likelihood, where the big difference is that it's n on the denominator here rather than n minus k. It gets more complicated than that, but I think that basic difference in these two formulas is enough for you to hang on to for the time being. Maximum likelihood estimates of variance do not take into account how many fixed effects had to be figured out in order to have that variance left over. It's analogous to when you were back in intro stat and the first formulas that you learned for computing variance had a population version and a sample version. ML is the population version and REML is the sample version. Why do we care? Because the estimates of the variances are going to be downwardly biased, meaning too small, in the use of maximum likelihood, particularly in designs where you have very few clusters. So REML is better from that perspective of having less biased variances, and we want to use that whenever we have smaller samples. If you have a sample that gets to be big enough relative to the number of fixed effects that you're adding, then it doesn't matter as much. So this is one additional layer of complexity you have to keep in mind, because which likelihood ratio tests you can do to add model parameters depends on which of these you're in. I have a couple slides about this. Just these are more for your reference in terms of the rules at play. But what I'm going to teach you to do will work without you having to memorize most of the rules. That is, whenever we are going to add something to the model for the variance, so whenever we add a random intercept variance or what is going to become a random slope variance, we are going to keep the fixed effects part of the model exactly the same. So whatever predictors you have, whatever coefficients they have, all of that stays the same when we add stuff to the model for the variance. Then we can compare -2 log likelihood from the two different models, whether we're using REML or ML. If you're using REML, you have to do it that way. If you're using maximum likelihood, you don't. But in order to keep this relatively straightforward, I will try to use REML whenever possible, and we'll follow the rules of this by keeping the model for the means constant, just changing out what's in the model for the variance. So this is sort of more than you need at the moment, but I figured I may as well just introduce it because it's going to stay with us throughout the semester. All right, lost my mouse. Come back here, Mr. Mouse. There it goes. You'd think with a giant mouse that it would like figure out where it goes, but now it's not letting me go back to the other screen. That's all right. I got a keyboard. Come on. Come on. 1 second, friends. Good. Okay. No worries. Skipping over that. Okay. How about we talk predictors? That's way more fun than likelihood, right? Yeah, and if you think likelihood is more fun than predictors, you're probably in the wrong class. I would direct you to the stat department or the biostat department, where likelihoods are the fun part. Not so much for me. So the good news, when it comes to level 2 predictors, everything you've already learned directly applies, and there's not very much additional complexity. So for example, let's say that I'm working with the same Snyder's and Bosker example dataset where I have level 1 students nested in level 2 schools as my clusters, and I'm trying to predict their language outcomes. And I want to add in 2 different school predictors. One is the amount of homework that the school tends to assign on some kind of average, and yes, this is totally made up data, and whether or not the school has grades that are mixed together in the same classrooms. So these are school level predictors that I would put into my model here. So at level 1, nothing is different than what it used to be. We don't have any child level predictors in the story yet. At level 2, what we had before is what I am now going to use the term unconditional to describe, meaning before conditioning on any predictors. That means that this U0 represents all of the variance that there is to be had. So U0 is each individual school's random intercept, It's in the model to represent the idea that we have a variance across schools and what the random intercepts is. So the variance itself is denoted as tau squared with the subscript for what it's the variance of, which is the U0, and it's in the equation to highlight that idea. If I want to stick in level 2 predictors, no problem. So what I'm predicting is how each school gets its own intercept, which at this point just means the school's mean. I had gamma 0, 0 here, and now you see I've got 2 more red gammas that end in a 1 and a 2. So this would be a good point to explain the subscripts. The first subscript keeps track of which beta in the level 1 equation you're trying to predict. So because all of these terms in here are trying to predict beta 0, they all start with 0. 00, 01, and then UO. The second subscript is an index for which predictor in that beta's equation you're at in the level 2 model. So homework is the first predictor of beta 0, mixed grade is the second predictor of beta 0, and you'll note they have C subscripts only because they only vary across clusters, which is schools in this example. They don't get P's, otherwise they would need to go into the level 1 equation instead because they're not per person. So at this point, then, after controlling for the amount of homework and whether each school has mixed grades, the U has a different interpretation. It's now the idea of a residual, of a leftover. It's what is the remaining deviation that is needed to get to each school's mean after controlling for the predictors that are in the model. For that reason, some textbooks refer to these U's, once they're part of an equation that has predictors in them, as level 2 residuals. I'm not going to do that to you. I will continue to use the idea of leftover in that terminology because that's what this is. It's the idea that U is what's left after controlling for the predictors. Each school still gets their own, but part of what makes it their own is in common for schools that are of the same kind. And note that homework is a quantitative variable. I have it centered at 2, which was near the mean of whatever fake scale this is. And I'll show you that, not this one in the code, but I'll show you how to center predictors. It's just centering a constant just like you would do in any standard linear model. And that's pretty much it. You put the predictors in the model, you see if their fixed effects are significant, you evaluate effect size, and you go about your business. Question, can I say again why there is no P? Yes. Because the story for today is level 2 cluster predictors, and P stands for person, which is level 1. So the amount of homework a school assigns on average is what this variable represents, and that is a school characteristic that is constant across the people from the same school. That's why it doesn't get a P. Same thing with whether or not the school includes mixed grades. No P there because it's not a person thing. To make sure I have this right, U is what is left over after adding the predictors. Yes, that is correct. So this U up here in the unconditional model represents the idea of this is all the reasons why some schools have better language scores on average. Cool. Now I'm testing a hypothesis that part of a reason why a school might have better language scores than other schools on average is because they assign more homework and maybe because they have mixed grades. Assuming mixed grades are a good thing, I don't know. So then this U is all the reasons, conceptually, it represents all the reasons why some schools still have a higher outcome than other schools after controlling for the predictors in the model. Adjusting for those predictors, the same idea as in a standard linear model. Okay, 2 thank yous. That means I must have answered the question sufficiently. Other questions? All right, so I'll show you what happens. Here's the code that it took to do this, by the way. New parts relative to the empty model from before are highlighted in yellow. So I have a whole separate example that I'll show you, but I left this code in here in case you want to see it from other packages. I'm not emphasizing. So here's some SAS output that we had from the empty model, unconditional model, before adding the predictors. So this is my fixed intercept here in the red box, and then these are my variance components, piles of variance in the blue box. Now I add my quantitative predictor for how much homework they tend to assign on average and whether the school has a mixed grade. And here's the solution. So if I go through the fixed effects, the intercept here has changed a little bit. Not a whole lot in this case, but it will change. It has to, because it means something different. So what's the difference between the intercept of 41 over here and the intercept of 41.5 on this side? Not a trick question, just a linear models review. Remember on the first day I asked you what's an intercept? This is a rejoinder to that. Vladimir, go for it.
Yeah, I think that in this left side we have that 41 is the mean of cluster means. However, after adding the level 2 predictors, that is the mean of the cluster means specifically for those schools with homework equals 2 that are part of our reference group. The mixed grading or the other one?
Yeah, mixed grade equals 0, which means it's not mixed, is the way I coded that.
Okay,
So
yes.
yep, exactly right. And as it says in the chat, 41 doesn't take into account homework or mixed grades. Yeah. So this is a conditional mean. That's another way to think about it. Whereas this one over here on the left is unconditional. So 41.08 is the mean of the cluster means, period. 41.5 is the mean specifically for a school with a homework level of 2 and that does not use mixed grades. So same principles of linear models. The fixed intercept is your reference point for the data. Then these two slopes, looks like based on the p-value that homework doesn't seem to matter. Good news for those of you who don't like doing homework, am I right? Except this is in high school. So for every unit more homework whatever, language at the school level goes up by 0.5, which is a non-significant difference. Mixed grades, though, apparently, maybe not so good. Schools that use mixed grading have 2 points lower on average for this language outcome than schools that don't. And so note the way that I'm phrasing these interpretations. Schools who? Okay, that's not a coincidence because the level 2 model is all about cluster to cluster mean differences, or school differences in this case. So the term child or kid or pupil is not part of the story yet. Schools who assign more homework have non-significantly higher outcomes. Schools who use mixed grades have significantly lower outcomes than schools that don't. Okay. So then, this is a look at the screen and answer the question. Which of my two piles of variance should these predictors have reduced? This can be a finger question or it can be a chat window question. Level 2 or level 1? Yeah, votes for 2. And the numbers kind of gave it away too. Yes. The idea is that level 2 is your random intercept variance. That's all the reasons why some schools have higher means than others. These two level 2 school predictors are trying to answer the question, why do some schools have higher means than others? So they did reduce the random intercept variance, not much, but a little bit. Why does my mouse keep disappearing? Goodness gracious. I had it set up perfectly and everything. 1 second. Please? Okay, let me get over to this window. I'm over here, that's good. There we go. I don't know. There we go. So here's some words. Everything that I just said written down on the next slide for your reference. So we have a variance left over, and this looks like it's the old version of the slide that I updated, and it's not the old one. I had clarified the words on here between what actual means. I will repost this. This actual from the level 2 random intercept means from the empty model, so like what the U would have been before. Whereas actual down here means the actual observed Y from the data. So there's a slight difference in what actual means that I realized after writing this, and thank you for some of you who had comments about this, that I should clarify the terminology. So I will do that, and I've fixed the slide subsequently. So what if we ignored the clustering? Would we come to the same conclusions in terms of what the model should be for the data? You know that in simulation studies, but not in real data, so it can be instructive sometimes to look to see to what extent you would come up with the same answers. And on the left-hand side of slide 31 here is the solution from a standard general linear model What that means is one pile of variance. So this is a model that ignores clustering, assumes that students are independent. Over here on the right is the solution with the random intercept. So beyond just the differences in the model for the variance output here in the bottom, the fact that we have 2 piles instead of 1, you'll notice that basically every single other piece of output has changed. The fixed effects have changed. The standard errors have changed. The degrees of freedom have changed. And because the standard errors changed, the t-value changed. Because the degrees of freedom and the t-value changed, the p-value changed. It's all linked together. So on the left-hand side, for instance, it doesn't understand that all 3,500 and whatever kids are not equally contributing to these things. It's ignoring the difference in cluster size and trying to figure out what the effect of homework is, and it's not doing the weighting appropriately. So the coefficients are off to some extent because of that. Standard errors are off because the model doesn't understand that we have way fewer, smaller effective sample size. We have 191 schools is what's going into this, not 3,500 students. So the standard errors are way too small over here, and the degrees of freedom are way too small, way too big over here, excuse me, as well. So we would come to the same conclusions in terms of non-significant effect of homework 2, but a significant effect of mixed grade. But this one's actually approaching significance. So you can imagine a situation in which if you did the proper multi-level analysis, you would come to a different conclusion about your level 2 predictor. All right. A note about the degrees of freedom. I have a couple slides in here just for your reference about that. I don't need to dwell on it. In multi-level modeling, how to figure out what your denominator degrees of freedom is a thing. It's not straightforward because each cluster has a different number of persons in it, most likely, and there are different ways of taking that into account across methods. Another question, Vladimir, go for it.
Yes, I have one. And so we can use ML or REML as an estimation method. However, we know that we can also use the univariate wall test or the multivariate version to test fixed slopes, right?
Yes.
So what is the utility or usefulness of ML compared to REML? If we want to use REML, we can use the univariate or multivariate wall test to test the fixed slopes. When should we use ML instead of REML? That's my question.
Okay, so what he's referring to, so wall test is the idea of taking your estimate divided by a standard error, and that ratio is either treated as a t if you're using the degrees of freedom, or it's treated as a z if you don't. So like in generalized models, it's always z. In structural equation models, it's always z. So for fixed effects, for fixed slopes like this, you are allowed to stare at these p-values no problem, because for fixed slopes, a null hypothesis of 0 and the idea of a normal two-sided sampling distribution where the slopes could be negative, could be positive, is totally fine. So we can look at these p-values and directly say, yes, this one's not significant, this one is, by most standard alphas that people would use. As an alternative, what is supposed to be asymptotically equivalent once you get to a large enough sample size is to take the difference in -2 log likelihood before versus after you would add each of these predictors. So you could look at the log likelihood of the model with homework and compare it to the log likelihood of the model without it, and that could be a significance test as well. They're supposed to match. From what I've read, if you get in a situation where they don't match, I think the log likelihood test is supposed to be like the winner of the two. However, you can't do that while you're using residual maximum likelihood, which is what we're using here. If you're using residual maximum likelihood, you cannot compare models that differ in their slopes for your fixed effects. It's not valid. So the answer is I would probably almost always use wall tests if I'm concerned about sample size enough to be in the world of REML and enough to be in the world of degrees of freedom. If I'm in a type of model where REML is not possible, any kind of generalized model basically is where that ends up to, and path analysis where REML is not built into any of the software packages, then I might have to stick with log likelihood comparisons to answer some types of questions. Okay, does that help?
Awesome, thank you.
Okay.
Yes, thank you.
Excellent. All right, other questions? Okay, so where do these degrees of freedom come from? Just a note about that. In terms of multi-level models, you'll see a couple different kinds mentioned. One is residual, one is Satterthwaite, which is a person's name from like the 1940s, and another is Kenward Roger, which is two people. That came out in the late 80s or early 90s, I think. So I have a table here as to what is possible. I have a little bit of description out of both. What you will see in all of my examples, including my textbook, is the use of Satterthwaite because it tends to be the most common across all different packages, and I like to try to make my results match whenever I can. It is analogous to corrections degrees of freedom that were developed for t-tests given unequal group sizes and unequal group variances. It kind of takes that idea forward. The idea is that it tries to take into account the dependency, the relative amount of variability at level 2 versus 1, as well as the relative sample sizes. Beyond that, it's an ugly matrix equation that I probably would not do a good enough job explaining, so I'm not going to try. But Satterthwaite is a person's name. It's old and it's well established. So that tends to be what I think people would recommend. The alternative to that is KR, Kenward Roger, two people. This is the same as Satterthwaite with an extra correction added to it for what the variances are estimated to be. In small samples, you don't get a very good estimate of your variance, and so it kind of like makes it a little bit bigger to try to overcome any downward bias, and so that can change your standard errors as well. So I will point out that this distinction of whether you need degrees of freedom or not really starts to go away once you get enough of a sample. So just as an example, if I have degrees of freedom of 20, then the critical value that I would look for to make sure p is less than 0.05 for my fixed slope would be 2.086. Whereas if I'm like, screw it, I don't even care what degrees of freedom are, I just use a value, that's 1.96. So in very few situations would you be in between the two where you would come to a different conclusion. So a lot of the literature talking about degrees of freedom in multi-level models comes from like super, super small designs, like in agriculture, where you have like 4 plots of corn or like, 6 sets of cows or something. In these kinds of settings where we have people in classrooms and, longitudinal and all that, it's not as much of an issue until you get into teeny tiny sample sizes. But wanted you to have just a sense of what that is, because sometimes Satterthwaite degrees of freedom have decimal values in them. They're not always integers, which can look a little weird. You can just say that you use Satterthwaite and not dwell on it usually in a printed report. All right, so that's a little bit about standard errors, p-values, degrees of freedom. In terms of effect size, so just as you would learn in any linear model, just reporting whether something is significant or not is completely inadequate. We need to pay attention to the size of the effect in a more absolute sense. The same types of tools are available to you to do that as in any standard linear model where you have normal residuals at least. You can take your t-value for your slope and compute a d-type statistic or a g-type statistic. I know there's a billion variants of this. Basically, there's a mean difference family and there's a correlation family. D is an example of the mean difference family. R is from the correlation family, and you can use your degrees of freedom and your T to compute that. So these are partial R's or partial D's. Nobody really uses that terminology, but in terms of how it maps onto what it means, it's partial, not semi-partial. You can also do explained variance. So the trick with these models is that you have to keep in mind that there's not just one variance anymore, there's at least 2. So in our present model, there's 2 sources of variability. There's why does each school still need its own mean after controlling for mixed grade and homework? That's level 2 random intercept. And then there's why do some kids have better language scores than others at the same school? Not controlling for anything yet, because that's coming next week. So there's 2 different approaches that I like to recommend for this, and they are complementary, meaning you can do both because they tell you different things. One is called pseudo R-square, and that is what it's called. That's not me being funny. And this is the idea of variance explained per pile, per variance component. So you would take whatever variance you're interested in, say the random intercept in this case, and get what it was before from the model with fewer parameters minus what it is now after you've added your predictors of interest, and then divide by what it was before. So this is then of the random intercept variance that you had before, what proportion of it did your two predictors account for? So it has an analogous interpretation as your regular variance explained. It's just of this particular kind of variance specifically. And you can't lose that aspect of it when you're talking about these things. This formula, by the way, is very straightforward. Anybody can calculate it. I have SAS macros that do this, and Jonathan wrote an R macro function thing that does this. The problem is that it can go negative. So rather than using two different models to compute this, an alternative that is increasing in popularity, these two articles are on your reference list and there's R packages that go with them. Reitz and Sturba developed an alternative version of this formula where the denominator is the model anticipated variance from the current model, the one with more. So they basically take the variance left over and then add back in how much variance must have been due to the fixed effects. So it's a different way of getting back to what the variance used to have been. It uses one model instead of two, and it has the advantage that it can't go negative because of that way of computation. So if you think it's R2MLM is one of the packages, you can feed it your results from R and it will spit all of these things out for you, which is very convenient. And I note that only the pseudo R square for the random intercept would be relevant in this case because we have level 2 predictors and that's what they should be targeting only, just level 2 random intercept variance. Okay, does that make sense? Still hear me okay? Say it's 1:12 and my microphone hasn't quit yet. Let me go ahead and jinx myself. Still there? Okay. All right, I dare you. Go ahead and quit on me. I got this. So this is one thing you can do per pile. The other, which is something that is helpful to kind of put it all back together again, and it's helpful once you get to models that are sufficiently complicated that you don't want to describe what happened to every single random effect, is something called total R square. And this is computed the exact same way as it could be in a linear model. You take the outcomes that you have, right? They're already in your data set. You ask your model to save the outcomes that are predicted from your fixed effects. Every software package has a built-in way to do this in 1 or 2 lines of code, and I'll show you how. That creates model predicted y hat values from the fixed effects only. And so you have a column of predicted y's, you have a column of actual y's. If you run a Pearson correlation between those two columns, that's R, you square it, that's total R square. So it is of the overall variance, right, of everything put together again, like the variance in language. Come back here, there we go. How much of it did your model account for? So this is more intuitive, I think, to people who don't understand multi-level models that well because it's one number. It also sort of washes over the fact that you have a lot more variability at the student level than the school level. So the values that we get out of this analysis, for example, are not very impressive. So this is what we had before. So my old residual variance at level 1 for student-to-student differences in language from the same school was 62. The extent of differences between schools in mean language was 17. That created an interclass correlation of 0.22. So we added 2 predictors at level 2, which meant that level 1 residual was about the same. Note that it's not exactly the same. It's about the same, and that's going to happen. It will wiggle a little bit, but it's basically no change, as we would expect. And the level 2 variance went down from 17.8 to 17.1. So not super impressive. If I plug those values into my R square, random intercept what it was minus what it is over what it was, I get a reduction of 3.6%. So this is not an R square for the model. This is an R square for the level 2 model specifically. So the way that I would talk about that, excuse me, is of the 22.3% of the variance in language that was due to school mean differences, of this 22%, 3.6 of that is because of differences due to mixed grade and homework amount. So it's 3.6% is explained of the 22.3%. Total R-square then, the correlation between the predicted outcomes from the fixed effects and the real ones is only 0.006, so 0.6% of the overall variance was explained. So not as impressive as 3%, but this is realistic. And I note here that if you're trying to compute total R-square for a paper that didn't give it to you, there's a way to approximate it. So if I have the amount of the interclass correlation, so here's 22% here, times the pseudo R-square for the intercept, plus the pseudo R-square for the residual, times 1 minus the ICC. Then you can put it back together again as a weighted average, and that's actually pretty close to what we actually got when we did it the right way. So there are many, many kinds of R-squares. It is essential, if you're going to use them, to explain which kind that you're using and how to compute it. That way your reviewers can follow you. Question from the chat. Can pseudo R-square be calculated for a non-normally distributed outcome? Oh, it can, but there's like 17 of them. So pseudo R-square is also a name that gets used for R-squares from, say, logistic regression or ordinal regression or analogous latent variable models that use those as a baseline. There's a bunch of different ways to compute it, and they don't agree. So then it becomes even more imperative, if you're going to use one of them, to defend why you picked that one and to describe which one specifically that it is. This is a whole thing. If you don't have a separately estimated level 1 residual variance, then there's no concrete way to say how much variance is explained. Everything has to be some kind of approximation, either using log likelihood values or, most of them use that. There's other variants of it. It's a whole thing. In the generalized modeling class this last time, I added an R package and a stata package to the logistic regression examples that lists all of them. So there's like literally 10 different ones that got spit out.
Lisa,
Yeah.
so would you need, it's like, if this is like if we're talking like IFA, like item factor analysis, would each, you know how there's like unique variants for each item?
There can
Would
be.
you, is that what you mean by you need one, like a separate one for, or is that something different?
So item factor analysis is predicting binary or ordinal outcomes using a latent predictor instead of a real one. And in those models, the model scale leftover variance, if you're in logits, is always 3.29, and if you're in probits is 1. So the R-square has to build off of that and try to anticipate what the variance would have to have been from the model with fewer predictors in order to still end up at 3.29 or 1. So it's still kind of pseudo-y, even though you have like this number, because the fact that the number can't be reduced based on the link function.
Okay, because it's basically rescaling that constant variance for to get back to like it makes sense what you said.
Yeah, it's the original price analogy. So I can explain that to you later on if you'd like, but that's a little bit beside the point at the moment. But if you've heard me talk about Coles and original prices, go to that as your go-to example for that idea.
Okay.
All right.
Thank you.
Sure. And it looks like, hey, we made it to the summary slide. Hooray! That's always exciting to see. 37 slides later. So MLMs begin with an empty model, always. That tells you how much of your variability is due to cluster mean differences versus within cluster variation. That sets you up to anticipate which kind of model predictors are going to be more useful. Come back, come back, come back. I know what it is. Every time I touch like one of the Zoom windows, then my mouse doesn't want to go back to the other screen. It's very weird. But if I do this, because this is already over here, then my mouse will come back. I win. We talked about ICC as a way to quantify an effect size for the amount of dependency due to cluster differences. ICCs in level 1 sample size play into design effects, which is your penalty function for how much extra people you need to overcome your clustering. And a little bit about significance tests and effect size here. So yeah, any questions before we look at an example? Another example, I should say. See how to make it work? That's always the fun part, right? when the answers show up, or you get numbers at all. That's always exciting. Okay, come on here. You can make it. Oh, it helps to turn your keyboard on. There we go. Okay, so this is example 2. Just as a reminder, all of the pieces that are in here are in the download folder. So on the course website, right underneath where this handout is posted, is a zip folder of original files. And this has the original data set, an Excel file that I used to make a bunch of different calculations. It has output in R and syntax in R, output and syntax in SAS, which are not in the handout, but I'm happy to answer questions about those as well if you want to use SAS, as well as output and syntax in Stata. So I don't put all of the output in the handouts. I try to limit it just to the part that is needed, but this has everything. And I also note in here there is a subfolder called R functions. I am giving those to you because I have permission. Jonathan wrote these functions. I don't know R well enough to write functions yet, and I kind of don't want to. But when he taught this class 2 years ago, he got tired of Excel spreadsheets real quick and decided to write his own functions. So he has one that's called pseudo R-squaredinator and total R-squaredinator. And yes, that's a lot of letters, I told him. And he's like, fine, you write your own function. I had asked for a birthday present, actually, last year, of a custom R package that computes all the things that I want. So this would be part of that. Maybe by my birthday next year, I'll have all the pieces going. But until then, I will borrow his. So the R program uses those functions as part of it, just as an FYI. So this example comes from the same data set that was used in one of the McNeish papers that's on your reading list. It's the one that is currently somewhere between under review and impress. I was reviewer 1, and I asked him if I could give it to you, and he said yes, so thank you, Dan McNeish. It discusses different ways of addressing clustering, including cluster-corrected standard errors, fixed effects, and random effects. And so he had demonstrated a bunch of models with that. It theoretically comes from the part of the high school and beyond data set that's been used in a bunch of different textbooks. It's another educational example. This time, though, we have more students, so 7,185 students from 160 schools. We're going to be predicting math from school characteristics of how big the school is, so just the number of students, and then whether the school is public or private. So 2 predictors in the level 2 model here. So first thing here, got to read in the data. I'm importing the Excel data that's in here in Stata and running some descriptive statistics so that I can get a sense of what I'm looking at. And this little box is actually from SAS because it's a little bit easier to paste and work around. But I'll note something interesting in here. Does anything in this little table indicate to you that perhaps these data aren't real? Because I was under the impression that they were until I looked at this table.
Is it the standard deviation of 604?
No, because that's how variable in size the schools are, which seemed plausible to me. No, there's one other number in here that gave me pause. Yen for the win. Yeah, the minimum math score is negative 2.8. Now, I don't know what scale this is, but I'm pretty sure it doesn't go negative. If you did that bad, like, you should just get a 0 and that's it. So, and the fact that the minimum is 100 suggests, that the sample was selected based on schools that had at least 100 people, which is a selection thing, not a thing. But this is a little bit curious, but that's okay. We'll roll with it. The first thing that I wanted to do is center my predictors. So private is already centered in the sense that 0 is public and 1 is private, so I can work with it like that. Size, however, I decided to not only center but also to rescale. So if we look at the size of the size, it is a mean of a little over 1,000 kids with a standard deviation of 600. If you think about what a unit is in that variable, the slope that we would estimate for school size would be the expected change in school mean math per 1 additional student. That's going to be a teeny tiny, tiny, tiny number. So to avoid that issue, I decided to rescale. So I subtracted 1,000 so that the reference is a school with 1,000, and then I divided by 100 so that it's per 100 students rather than per one student. So that just moves the numbers over a few decimal places so that everything is easier to keep track of. Then one last thing that I did here as a one thing that I want to make a comment on because we're coming back to it later in the semester. These models need all of your rows to be complete in order for those rows to be included in the analysis. That means, given that we're working with level 2 predictors, if any school is missing their school size variable or their private variable, they're getting kicked out of my analysis. So in order to maintain the exact same sample, regardless of what my particular model has in it at that moment, I'm selecting the data to have complete cases on the 3 variables that are building this handout. Math is the outcome and size and private as the predictors. Doing the same thing then in R, with my usual caveat that I'm not good at R and I don't like it. So if you know how to import data and do things in less code using tidyverse or what have you, knock yourself out. I really don't have a dog in that fight. I tend to use base R and to keep my code as transparent as possible so that people looking at it will know exactly what's happening. I find that to be most useful for folks who are just getting started, but that means that there's probably more writing in some cases than there needs to be, but I can live with that. So I'm creating
Lisa?
a working directory. Yes, where are you? There we are. Amanda, yes, go ahead.
Sorry. Did you say that you also have the SAS files? Are those available in the if I downloaded all of the actual files that this comes from?
Yes, in the zip folder is
Okay.
a SAS syntax and output.
Okay, awesome. Thanks.
Yep. Yeah, and I'm happy to answer questions about those. It's proc mixed. I used to do all 3 packages in my classes and it just became too much. And so SAS was the one that was the least popular, which is why I took it out of the examples. But because I'm already using SAS to check most of my work, I decided just to keep it in there. So yes, SAS files definitely available. And you can use SAS in your homework as well, because I'll be building the homework with SAS still. Question, is there a way to implement indexing in SAS to locate missing or non-missing data? Yeah. There's a whole bunch of functions. So there's nmiss for numeric variables and cmiss for strings or numeric, I think. I can direct you to some resources about that, but yes, you can do anything you want in SAS the same way that you can do anything you want in R. And apparently there's a fire on campus. My phone just told me. Anyone work at the Advanced Technology Lab? I hope not. All right, so here's some R stuff. I'm also loading in the functions that I mentioned that are in that subfolder, importing the data set from Excel, running describe, which is a function from the psych package that generates sample statistics, doing the same rescaling, and then doing the same selection based on completeness of the same 3 variables here. So just a little bit of data import stuff there. Any questions on the syntax to import data or the story?
I'd like just to make a point that I'm running like 20 models in Scan through the supercomputer, so I hope I'm not the cause of the fire.
I don't think that that's how that works, but I thought that we were using the computing stuff in the basement of Linquist Center anyway. Isn't there a supercomputer
Oh,
down
that's
there?
true.
Yeah, it might not be.
There's also one with Liberty, but
Yeah. Okay, so yeah, I don't think it's
Anyway.
anyone's fault here, but if anyone's near that building and you need to get out to be safe, please certainly do so. All right, so first thing, single level empty means without a random intercept model. So this is more of a demonstration. I don't normally start with this, but since that's the simplest model that we could start with, I figure why not? So I'm calling this model 0. So this is your first shot at using Stata mixed, most likely. So we have mixed and then the outcome after that. Right here, come back, right there, the blank spot is where the fixed effects would go. Yes, Nikki's excited about Stata mixed. I like Stata. I've gotten to like it more as I've used it. I'm not good enough to do all the behind the things thing, like to make macros and functions and like to have it do automated stuff, but I do like it for data analysis. After that is this weird part right here. So bar is you telling Stata, hey, now I'm talking about the random side of the model. That's what bar means. School ID is the column that identifies which rows go with which school. So it's a constant over students. It differs across clusters. And this little spot right here is where your random effects would go. In this model, I don't actually want the random intercept that is estimated by default. And so that's what no constant does here as an option. It shuts it off for the time being. So that one shuts off the random intercept. If you had the need to shut off a fixed intercept, that would actually need to come over here before we get to the random part of the story. After that, I'm asking it to make sure that it's using residual maximum likelihood, or REML. I am asking it to use degrees of freedom. So I believe this is not a default. Denominator degrees of freedom first showed up in Stata Mix around version 13 or 14, I think, and I believe it's still the case that they do not use it unless you ask for it. So I'm using the residual method for right now because that's the only one that it will let me use. DF table means show the degrees of freedom in the table along with the t-value and the p-value, and no log just means don't print the iteration history, which can get quite long in the output for models that iterate for a long time. So then this is the little chunk of output that I asked for. It tells you how many people you have, of course. It gives you log restricted likelihood. So I have a note here that this is the LL version that you would need to multiply by -2 in order to do likelihood ratio tests or things like that. That's why down here, I have a little chunk of code that prints it for you. So this accesses the stored results from the model and then just returns the -2 log likelihood. So when you get started on your first real homework, which will not be due next week, it will be due the following week, and it looks like it's going to have to be due on Wednesday, given that we're just now getting into this example. This homework system for every model that you answer is going to ask you for -2 log likelihood first. If you get -2 log likelihood correct, to the level of precision the homework system asks for, which is usually 2 decimal places, once you get that correct, you know you have the right model in terms of the right stuff in it. So that's why I always ask that first. If you don't have the right model, there's no sense in going forward because you know everything's going to be off at least to some extent. So regular flavor log likelihood is right here. The -2 version is added if you use this little chunk of code. Underscore const, that's my fixed intercept. It's 12, meaning this is the mean just across all the data of the math scores. So clusters are not part of the story yet. This model doesn't have a random intercept, so this is just the straight mean of this variable. And var residual here, this is the residual variance, or the variance of this variable across all the cases. So just mean and variance in my 2 parameters. It spits out AIC and BIC if you ask for it. In anticipation of the fact that we are going to have a level 2 model, I'm using level 2 sample size as the n. That way it will match what is done in other packages. In R, I am using GLS as a function from the NLME package. In the R script that's online, by the way, the first part of it loads all the packages. It checks to see if it's installed in your system and installs it if needed, and then loads it after installing it if it's already there. I have to use GLS if I want to get log likelihood. Otherwise, I could just use regular LM. The same with Stata, I could use regress instead, but it doesn't spit out log likelihood. So the data set it wants is called example 2. Model is where formula goes and other R packages, but it's analogous. Math squiggle 1 means I'd like 1 fixed intercept, please, and nothing else. So I asked for it to print -2 log likelihood specifically as -2 times the return of this function called loglike. So that spits out the value here, which agrees exactly with status. Love it when that happens. Gives me the AIC, the BIC, and the regular flavor log likelihood as well. And then here's my fixed intercept of 12. It gives me the residual standard error, which is like the residual standard deviation. And in order to get the variance out of that, you have to ask for it separately. So I did that down here by accessing part of the save results under sigma and asking for it to be squared. So that's that number here. So in R, sometimes you have to ask for extra pieces of information to get what the other programs provide by default. That's what I've learned. Okay, so we know this model is wrong. We know that, right? Because it ignores clustering. but it is a baseline with which to compare the alternative, which is adding clustering to the model, meaning adding a level 2 random intercept. So this is our baseline for comparison. So if I have now my 2-level model that adds my random intercept U right here, the Stata code looks exactly the same except for the removal of the option for no constant. Stata gives you a random intercept by default whenever you invoke this bar thing with the ID variable that the random intercept is to vary over. So everything looks very much the same, except now it understands grouping. So it prints out these helpful descriptive statistics for how many people you have per cluster. So an average of about 45 here, it looks like. The fixed intercept is close to what it was before, but it's a little different because this is now the mean of the cluster means rather than just the overall mean of the data set. And then we get our 2 variance components. So 8.6, as I have noted out here, is my random intercept variance, the variance of the constant as it is labeled in Stata. 39 is my residual variance, the variance of the ease across people from the same school. So adding these back together again would give us an estimate of the total variance of math, which will be close to, but not the same as what it was in the previous model. Okay.
Lisa, can you repeat that one more time, the 39.1?
Yes. 39.1 is labeled as variance of the residual, and I have notated that as the variance of the ease specifically. So 39 is all the reasons why some kids are better at math even if they go to the same school. 8.6 is all the reasons some schools are better at math on average than other schools. And these two are unrelated to each other because you can never have a covariance across things that are at different levels. That's like a by definition thing. Levels are orthogonal. And then this thing right here, LR test versus linear model. That's your likelihood ratio test. So what it is doing for you is comparing the -2 log likelihood from the model we just looked at without a random intercept to the one that we have now with the random intercept. The difference in -2 log likelihood is 986. So, pretty sizable. This chi-bar thing, as I noted here in the text, that corresponds to the idea of using a mixture distribution for your chi-square test, where it's a mixture of chi-square with the degrees of freedom 0, which would mean literally 0, or degrees of freedom 1, for when the random intercept variance would be positive. So it does the correct p-value for you because it understands that you're testing a variance that cannot go negative. So this is one case in which it outputs it correctly. If you had another way of computing it where you didn't have the mixture p-value, you can just cut it in half. And that's what I did in my Excel spreadsheet for this example as well. So here's where that math came from, by the way. 48,102 was the -2 log likelihood from the model without the random intercept, minus the one from the model with the random intercept, and that's where we get the 986 from. Last piece of information we would care about, our friend intraclass correlation. So the numerator of intraclass correlation is the random intercept variance at level 2. The denominator is that plus the residual variance at level 1. So 0.18. 139. What's 0.18 mean, folks? Interclass correlation of 0.18. Let's throw some words on that.
So 18% of the variation is due to between cluster variation.
Yep. 18% is between.
Okay.
Between what? Clusters in this case. Yep, the percent of variation due to clusters, absolutely right. If I wanted to put it into the word correlation instead of percents of variance, how could I talk about this as a correlation? 0.18 as a correlation. Vladimir, go for it.
Yeah, that would be the average correlation of two students from the same cluster.
Yep, that's how correlated students from the same cluster are. And you can think of it as an average because you're assuming that all clusters have the same residual variance, which is a testable assumption, but one that's very commonly made, especially when you're first getting started in your modeling. So yeah. So that's not a lot, but it's not nothing, for sure. In terms of ICC2, I could not find a way to do that directly in Stata, and I could not figure out how to make Stata save the numbers to compute it internally, so I gave up, and I just wrote out the formula myself. So sometimes you just got to turn it into a calculator to get the job done. So ICC2 looks a lot like ICC1 with the exception of dividing by the level 1 sample size, which is right here, and that gives us a value of 908. So cluster means are relatively reliable when you have a mean of 45 kids per school, as you might imagine. All right, R output, and then we'll call it a day. I am switching in R to a different package. So I'm using LME4 and specifically the function elmer in it. The reason I'm doing that is because I have found Elmer does Satterthwaite degrees of freedom much more reliably and across a greater variety of models. In the other longitudinal class, I also used the LME function with an LME because that had more choices for the R matrix, for residual variances being heterogeneous or having residual covariance. That's not a thing in clustered models. Like, you will never change your R matrix because people from the same school, people from the same cluster more generally, are viewed as exchangeable. So we can use Elmer for everything unless you wanted to estimate some kind of heterogeneous residual variance, in which case it doesn't have that built in as far as I know. So that means the syntax looks a little bit different than it did before, but this is what it's going to look like for most of the semester. REML equals true, make sure that we're using that as our estimation. Formula then is where we put the linear model. So math is the outcome. Squiggle 1 here means I'd like one fixed intercept, plus in parentheses with the bar thing, that's the random part of the model. So only a 1 before the bar thing means that we're asking for a random intercept only, and it's random across school ID as the ID variable for my level 2 units. I am asking it to print -2 log likelihood and AIC and BIC in addition to the summary. So the first thing it spits out is regular flavor log likelihood. The value that is labeled right here under deviance, that's -2 log likelihood. So if you're doing your homework in R, this is where you come to get your -2 log likelihood with enough precision to enter it into the homework system. Then we get random effects. So note that this label is not super great. How many random effects are in my model? Finger question. How many random effects are in my model right now? 1. I have an intercept. Yet there's 2 entries in the table called random effects. So you can think of this label as model for the variance, right, instead. It's not just random, it lists everything. So school ID intercept, that's my random intercept variance. That's the 8 that we saw on the previous page. And then 39 is the residual variance, the variance of the E's. And by the way, anything out here in bold is me being nice to you. This does not show up on your output. This is me just trying to help you find where the numbers are that you need to pay attention to. There's my fixed intercept, as before, the mean of the cluster means. 2 additional commands that I'm using here. ICC, which is a function from a separate package called performance that I included, and that computes your adjusted or unadjusted ICC. It takes out the predictors to create an adjusted version, but since there's no predictors yet, it's the same. So there's our correlation of 0.18 for students from the same school. And then RANOVA, which is how you do likelihood ratio tests when you're using Elmer. What it does basically is go through iteratively and take out each random effect and compute the log likelihood for the model without it, and then do a comparison for you. So in this case, we have what the -2 log likelihood would have been for the model with the random effect, so nothing removed, versus the model where the random intercept was removed instead. So note these values in the table, these are log likelihoods. I have the -2 version of this then over here. So model without it, minus the model that has it. Since this is minus minus, it's a plus, times minus 2. That's where you get the same 986. Last but not least, ICC2, there are two functions that I found that use LME to do this, and so the weighted versus unweighted gives us slightly different estimates of reliability, but different in the third decimal place. Okay, 146. Time to wrap up for the week, because it's Thursday. It's not garbage day here, and that's how I know that. Especially now, I can't even blame it on the pandemic. I'm the only pandemic in town, apparently. Any questions before we call it a week? Feeling good? All right, well, I'll hang out for a few minutes as usual if anybody wants to talk to me. Otherwise, thanks for being here. I hope to see you in person on Tuesday. I'll let you know if not. All right, have good weekends, folks. Take care.
I just wanted to say